Okay, today we are going to problem 6, 7, 9, 17, and 20 of chapter 3. And first, problem 6, 2-point charge Q and positive Q and negative Q are located on the z-axis at positive A and negative A, respectively. Part A, find the electrostatic potential as an expansion in spherical harmonics and powers of R for both R larger than A and smaller than A. And first, we write down our potential in the general form, and the x1 is the location vector of positive Q, and the x2 is the location vector of negative Q. And we expand the 1 over R in the spherical harmonics like this. And since the symmetry n equals to, that means n equals to 0. And next our spherical harmonics can reduce to, can drop into this polynomial. And this one has a relation here, and this one has a relation here, and we can drop into this again. And that means for even part, for L is an even integer, the coefficient here is 0. So that means only the odd integer will survive. So here we can write down our potential in this form. This is for part A. And part B, keeping the product constant QA defined as P divided by 2. Take the limit of A approaching to 0 and find the potential for R not equal to 0. This is by definition a dipole along the z-axis and its potential. Okay, so we hold QA equals to P over divided by 2 as a constant and take limit A approach to 0. And we look back for our potential here. And because we are looking into the origin point, so we take the smaller r is our no. We take the limit of A approach to 0. That means our position constant. Our position of the potential constant should be far away from the charges location. Okay, so the smaller r here we take A, radius A, and the larger r here we take the position R. Okay, and we hold QA equals to P divided by 2 here. We take out 1A inside the summation here. We take out the 1A here, and we write down our summation 1 by 1 and take a limit A approach to 0. So we only the first term survived here. Okay, and P1 of cosine theta will give us cosine theta here. Okay, so the answer for part B is here. And part C, suppose now that the dipole of part B is surrounded by a grounded spherical shell of radius B. Concentric with the origin. By linear superposition, find the potential everywhere inside the shell. Okay, so the new potential will like this. Okay, this is our dipole term, and the shell in the new potential given by spherical shell here is like this. And we have the boundary condition because this is a grounded shell, so the potential on the shell should be 0 here, and we just 0 equals to this one plus this one. So we take this term to the left side. So we have a relation here. And because only the P1 term survives, so we will have the relation here, and only the coefficient A1 survive. And next, finally, and after our boundary condition matching, we will get the answer here. After grounded spherical shell adding, we have the new potential here. And this is for part C. And we go to next, problem 7. 3-point charge are located in a straight line with separation A and with the middle charge at the origin of the grounded conducting spherical shell of radius B, as indicated in sketch here. For part A, write down the potential of the 3 charges in the absence of the grounded sphere. Find the limit form of the potential as A approaches to 0, but the product QA square we hold as Q remains finite. Write this later answer in spherical coordinates, and the same we following the same steps as the last page, and we just do the same calculation, and finally we'll get the answer here. And next, this is for part A. And next, again we added the spherical shell back, and they induce image charge to hold the boundary condition. Okay, because we added this grounded conducting spherical shell. So okay, so we should do some image charge here, and here because the minus 2q is located at the origin, so its image charge is just at the origin. It just at the origin here. Okay, and again we take the limit A approach to 0. So our R just for much larger than A. Okay, so we do just nothing special. We just do the same calculate, and this one is our real charge potential, and this left is our image charge potential. And we take the smaller r is A, we take larger r is R, position R, and just do the and make A approach to 0. So many terms will collapse into 0, and only the first term survives here. Okay, only the L equals to 2 terms survive here. So the answer is here. And here we have another solution. We have another approach here. So the second approach, we use the fact that the potential on the boundary should be 0 here, and we use the same steps as the last 2 page. We use the same step, following the same steps the last 2 page, and we will get the coefficient AL should be here, should be like this, and the same, only L equals to 2 terms will survive. So we will have the answer here. Okay, this is for problem 7. And for problem 9, a hollow right circular cylinder of radius B has its axis coincident with the z-axis and its ends at z equals to 0 and L. The potential on the end faces is 0, while the potential on the cylindrical surface is given as V and is related to his face and z Z position. Using the appropriate separation of variables in cylindrical coordinates, find a series solution for the potential anywhere inside the cylinder. And just, we have a general solution here. And we use the boundary conditions, and we can drop our general solution into this form. And this is our boundary condition on the walls here. And next we use a boundary condition on the ends, on the two ends. It should be equals to function z potential function of phase and the z position. Okay, and we do orthogonal integral, and we will get the answer here. We will finally have the coefficient Cmn and Dmn here, and that means our unknown are all downs. Okay, so here is our series. This is our series solution for the potential inside the cylinder here, with the coefficient C and D have the relation here. Okay, this is for problem 9. And for problem 17, the Dirichlet green function for the unbounded space between the planes at the two ends allows discussion of a point charge or a distribution of charge between parallel conducting planes had in zero potential. For part A, using cylindrical coordinates, and showed that one form of the green function is like this. And here we start the heavy calculation. And the differential equation here, we have the relation here. The Laplace green function should be like this. And eigenfunction in this direction, we can do some quick steps, and we change our z directions component into sine n pi z divided by L, and the phase direction into exponential of in phi. And our green function has an easy form like this, and we next should be deal with the coefficient here. Okay, and we use the relation this Laplace green function should be equals to this one, and Laplace we have the raw component, raw Laplace, and this one is for our z Laplace, not our phase Laplace, and this term is given by our z Laplace. Okay, so next, the completeness relation of our phase and z direction, we have these two relations, and we use back, we imply this relation into our Laplace green function here. And finally, we will get our A coefficient has a form like this, and it is associated with a radius function here. And next, we will deal with the rho function here, and we do the final sorting, and we will get the GMN has a relation like this. And next, we will change our base. We change our rho into z, and we can cancel this. We can absorb this term into 1. Okay, we change our rho into z into x direction, into x coefficient, not direction, into x coefficient. And we have a relation here by this. And next, we modify Bessel equation with boundary condition G, and they are finite for x smaller than x prime or x larger than x prime. And we have two approaching from negative direction or for positive direction, and we have this and we use the boundary condition here. And finally, we'll get the coefficient A and B. Okay, so and next we can. So the final, the modified Bessel function satisfy the Wronskian formula here, and do an integral into long x and the 1 divided by x, and then it should be equals to the relation we have calculated this page. And finally, the GM, we have the result here, the function of our radius position has a relation here, has a formula here. Okay, so finally, our green function has a form like this. That is equals to our part A. Hey, yeah, we just do the heavy mathematics. Okay, we just keep matching our boundary and just change our base and just the heavy calculate. And for part B, we need to do another calculate and following the similar steps like the last 4 page. We just do the similar steps. Okay, so just first we use the complex relation rho and phi. Here we use rho and phi. For part A, we use z and phi. Here we use rho and phi, and we have another relation here. And next, we change our delta. We have these 2 relations here in part B. And again, Laplace green function equals to this one and equals to our delta functions. Okay, and this one, and we just change our integral. We use the similar integral, and we have the B. We have a B coefficient. We're like this, and again the G function show up here. And next, we deal with the G function and just do the calculation and sorting. We have the differential equation like this. And again, with the boundary condition, we have a 2 approach. We have two direction approach. And next, the same calculation, we match the boundary condition, and finally we'll get the answer here. Yeah, it is a heavy mathematics. Okay, and for part B, the answer is here. And we go to the last problem. For 20, from the results for the last problem, from first principle show that the potential at a point charge Q between two infinite parallel conducting planes held at 0 potential can be written as like this, and where the planes are at z equals to 0 and the L and the charge is on the z-axis at the point z equals to z0. So we can start from our formula from problem 17. Okay, and we use a green theorem, and we can easily get the answer here. Okay, so here we don't need to do some heavy mathematics. We just do the green theorem, and we will get the answer easily like this. Okay. And next, for part B, calculate the induced surface charge density rho 0 and rho L on two ends, on two plates. The result for the upper place will like this. Okay, so we just do the what's that, the boundary condition, the difference up, the difference between the two sides of the plate, the potential, the different partial potential difference two sides of the plate, we will get the surface charge density here. Okay, so since we have get the potential for this space, and we just do a partial z at the surface. Okay, we will get the charge density on the lower place and the upper place here. Okay. And next, for part C, from the answer in part B, calculate the total charge QL on the plate. QL is the upper plate, the total charge upper plate on the plate by summing the Fourier series or by other means of comparison. Check your answers again in the problem 13. Okay, for total charge on the upper plate, we can integrate over the charge density over the space over the plate, and finally get the, and we will get the integration here, and we should deal with this integration, and we use the relation here, and we can drop our integration into these terms, and again we use the summation relation here. We change these terms into this one, and finally the answer get here. So the problems are all finished. So we can see you next time.